Thank you very much. Starting on the existing protocol. My name is Michael Awe. I'm representing my supervisors who are not here. Professor Avleen Malhi, Dr. Nicholas Mavengere, and Professor Marcin Budka, and also Dr. Bhargav, who is from Avleen. And I'll be presenting my research work, which is titled Towards Automation of Last Planner Systems. Here is a brief outline of my presentation today. I'll be talking on the introduction all the way to a conclusion where I discussed the study that the study lays the foundation for automating last planner systems and integration of artificial intelligence in last planner system. So the question, to kick off, I'd just like to ask the question, why are we somewhat automating last planner system? And why are we integrating artificial intelligence in this? The answer is not far-fetched. It's just to be able, because the kind of projects that are being taken on these days in construction are kind of expanding immensely in scope and increasing in variabilities and uncertainties. And you can see in the kind of projects that are being taken on these days, some of them very high in complexity, and some of them even abandoned. And also McKinsey mentioned in the report that 98% of projects that are taken on these days are either completed with delays or cost overruns. And so there is a need, right? There's a need to sort of find improved systems, improved planning and scheduling systems that are intuitive and that can be reliable. And this goes to show like the main motivating factor for this particular research is to be able to generate accurate look-ahead schedules, right? And if you look at the role play on the right, where you see a planner who is being saddled with the responsibility to come up with certain look-ahead schedules and does that, but at the point of execution finds that none of these tasks would actually be completed due to one constraint or the other. And so this is like the main issue and the main challenge. And this is actually also in parallel with the main challenge, which is in parallel between digitally implemented last planner systems and also manual implemented last planner systems. So this other challenges also includes, aside incorrect look-ahead planning or schedules, other challenges include inability to manage project variability correctly, also limited constraint management, data management challenges, and others. So as regarding the research gap, which actually ties and aligns with the objectives for this particular research, the research gap shows that many researches existing in repository shows that most projects have actually just worked on using mismatch of planning technologies to be able to do some form of automation, but they have completely neglected the three major aspects of a functional last planner system. And so, this then leads to, the objectives for this particular work, which is to kind of create a lean predictive model, which is able to overcome delay in construction projects. Basically, to just automate the digital last planner system. So, a last planner system is a system that contains three functional aspects, which is the constraint aspect, the communication aspect, and the schedule management aspect. Right, and so to be able to integrate data processes and integrate data within these three functional aspects is really important, as that is what is going to lead to a pathway towards automation of last planner systems. So, if we are to consider a schedule with a list of tasks, as can be seen on the table over there, and a constraint of list of constraints as on the table or just under it, to be able to generate specific lookalike schedules which are constraint free and which fit into a specific lookalike period is given by the objective function as max z and are subject to the function and are subject to the following four constraints. So on a broader note, we also presented a framework that shows how the data within the three major functional aspects of a last planner system can kind of be integrated in such a way that we can reach automation, a full automated last planner system. And some of these techniques include the self-querying, deep learning, RAGs, and of more recent like MCPs and agents that we have. But to dig that deep, we looked at constraint resolution prediction, and we used about 173 constraints of a large multi-stage project, basically a data science, but a data center. But I cannot speak so much on that because there's an IP on that. And also we then use the architecture as found just underneath to be able to model the constraint resolution duration. We use certain features such as constraint complexity score, which is also derived from other features such as deadline date detection, sentiment analysis, and structural features of the constraints themselves. So overall, okay, just on top, we have like a sample of some of the constraints that we have there. And the results basically show that the neural network mean absolute error was 23.18 days away from the average test instances. And we also looked at other models with like the SVR, like GBM and random forest. SVR seemed to have performed a little well in the sense that the absolute mean absolute error was 21.78, but the MSE and the RMC were significantly higher than that of neural networks. In terms of limitation, the data size was somewhat small, and also there were some distorted representation and structural inconsistencies in the data set, but that was improved using some processing tools that we use to process the data set. In terms of recommendation, we anticipate that constraint resolution times with a predictive model reduces the need for frequent planning and avoid productivity loss. So I'd recommend that this kind of model be used because the more we use the data, the model, the more the model performs well. So in conclusion, the research augments the last planner system by optimizing lookalike scheduling and predicts constraints resolution duration. For future works, we hope to refine the optimization representation into a constraint iteration framework, embedding implicit and explicit functions into LLMs, LLM structures for better integration with RAG architectures. And we also intend to use like other techniques such as TAPAS, which is table parsing, and self-querying. Here are my references. This work was supported by Beaumont University and Visilin under a match-funded scholarship program. And I also acknowledge the contributions of my supervisors for their constructive comments during this work. Thank you very much. I'll be happy to take questions. And also regarding future works, if anyone was interested in integrating LLMs, MCPs, or agents, I mean, in automated scheduling or schedule generation, kindly reach out. I'll be happy to collaborate. Thank you.